Okay, let's get going with the second talk today, and it's a pleasure to introduce Professor Carlos Simpson. And he's going to be speaking about secondary Kodaira-Spencer classes and nonabelian local monodromy for simply connected families. Carlos, thank you so much.
Okay, I guess I hope everybody can hear me. So
Very well,
thank
yeah.
you. Yeah, thank you very much for the invitation to speak. I'm sad not to be in Miami, but yes, yeah, sometime soon, I hope. Yeah, so also let me see if I can turn this into full screen mode. Just a second. Uh, uh, is that okay for the screen,
Yeah,
Ernesto?
very good.
Okay, good. So yeah, so I'd like to talk today about secondary Kodaira-Spencer classes and kind of a corresponding concept that happens when we have a family of simply connected varieties. Of course, the non-simply connected case is obviously something to look at in the future. So yeah. Oops. Wait a second, what's going on? Okay, so suppose we have a smooth projected morphism of smooth complex varieties. Um, and we look at a point in the that should be an S. I'm sorry. Look at a point in the base that should be S. Sorry about that. So then the classical Kodaira-Spencer class is the map from the tangent space of the base into the deformation space of the fiber, which is H1 of X Tx. Um, And this tells us the first order deformations of the fiber variety XS induced by tangent vectors in the base. And then this acts on Dolbeault cohomology. So the Dolbeault cohomology is the direct sum of HQ of omega p, and it acts just by cut product. So cut product is going to increase the Q value and decrease the P value by one. Uh, we contract the tangent space with the differential form. Um, and we get a map from the tangent space into the endomorphism of the Dolbeault cohomology. Um, this is basic stuff, which I learned from Philip Griffiths in his class. I know this is like my main connection with Don Spencer. Really, is this whole concept, which I learned from Phil. So then this Kodaira-Spencer map decomposes as a direct sum of maps from HQ omega p to HQ plus one omega p minus one. Um, and we call these the Kodaira-Spencer maps, and they play a crucial role in the theory of variations of Hodge structure, as I think everybody knows. Um, and these tell you how the Hodge filtration varies as you move in the base with respect to the fixed frame that locally that you get by using the flat Gauss-Manin connection on the family of de Rham cohomology groups of the fibers. So our goal here is going to be to extend this theory a little bit and into higher homotopy. Okay, so we can view this as a Higgs field in the sense that we can take the tangent space on the left side and turn it into the cotangent space on the right side and globalize over the base. And so we can view this as a map from EP into EP minus one tensor omega 1s. And it gives us the bundle E, which is the direct sum of these EPs. It's the relative Dolbeault cohomology that makes it into a Higgs bundle. This is, you might say, one of the first examples of Higgs bundles, although it wasn't recognized as such. Then from a very long time ago, from I think Spencer's contributions and Griffith's contributions to the theory of variations of Hodge structure. And it also, historically, it appeared pretty explicitly in Steve Zucker's paper about L2 cohomology, which came itself from some letters from Deligne to Steve Zucker. Um, Okay, so and then I think as you all know, the Dolbeault bundle is the associated gradient of the de Rham bundle with respect to the Hodge filtration, and kappa is the map that's induced by the Gauss-Manin connection. Uh, so now we can also, instead of looking at just the cohomology, we can look at the family of de Rham homotopy types of the fibers as S varies over the base, and this is really should be considered as a higher stack. And so it has what you might call the Gauss-Manin connection also that was first introduced by Navarro-Asna. Um, and it has an nonabelian Hodge filtration, which can be thought of as a family parameterized by the affine line that's GM equivariant. And the associated graded, or the fiber over zero, is the family of Dolbeault homotopy types of the fibers. And now the Kodaira-Spencer map is going to give you an action of the tangent space on the Dolbeault homotopy type of the fiber. And of course, on each of the Dolbeault cohomology groups, this induces the usual Kodaira-Spencer actions on the cohomology. And similarly, on the homotopy groups, you could also turn those into families with a Gauss-Mini connection, and you get a Kodaira-Spencer action on those things also. I think it's well known that those will form a variation of mixed Hodge structure, and this is again the Kodaira-Spencer map for the graded of the Hodge filtration in that variation of mixed Hodge structure. So the observation here, which we might be interested in, is suppose the base is higher dimensional, not just a curve, but a variety. Then it might be the case that these Kodaira-Spencer map actions on the actual invariants, the homotopy or cohomology groups of the fiber, might actually be trivial. And in that case, we can still get some secondary Kodaira-Spencer classes corresponding to the action of the tangent space, but in higher homotopy. And that's what will be the first part of our discussion today. And then the second part of the discussion is that a very similar phenomenon is going to occur at the singular points when you have a logarithmic Gauss-Mini connection. So if you have a singular family, which is, let's say, semistable, then you have a logarithmic Gauss-Mini connection, and the residue of logarithmic Gauss-Mini connection is also going to again be an action of an abelian group. In the higher dimensional case, it will be a higher rank abelian group also, and this will have a similar type of a secondary invariant structure. So that's what I'd like to talk about. Okay, so to get started, let's first discuss the Rham formal groupoid. So we're going to sort of bypass complicated calculations of rational homotopy theory by instead using a stacky type of a viewpoint. So this is the way we start. So suppose we have so we'll be looking at a smooth projective morphism of smooth complex varieties, and assuming that the fibers are simply connected. Then let's look on the base. We can define the Rham formal groupoid, which is the groupoid object in the category of formal schemes. I'll have a picture on the next slide here. But the words here are that it's a groupoid object in the category of formal schemes whose object is just S, and whose morphism object is the formal completion of the diagonal. And so we think of the morphism elements of this groupoid as being links gluing together points of S which are infinitesimally close to each other. So this is the picture. So the picture here is that each point gets glued together to all of its infinitesimally close points. So that's these little links that are drawn on the bottom here. And if you draw in S cross S, if you draw the places where you get these links, that's really what this light blue stuff is supposed to be the formal completion of the diagonal. So we take, if you have a category, it has a set of objects and it has a set of morphisms, right? And the set of morphisms maps to objects cross objects by the source and target map, okay? In this case, we're going to be considering this special situation is where that map is injective. So between any two objects, there exists at most one morphism. And we'll say that there's a morphism exactly if the two objects are both infinitesimally close together points. Which is to say, if that point in S cross S is in the formal neighborhood of the diagonal. Okay, so that's the picture. And like roughly speaking, the idea is we're going to try to form a topological space out of S by kind of identifying infinitesimally close points. And actually, if you're interested in like Bourbaki things, there's some kind of notion of like uniform space or something like that, where you have like a space, and instead of a topology, you have sort of a germ of neighborhoods of the diagonal in the set, and that this is sort of algebraic geometry, formal algebraic geometry version of that concept. Um, Also, I should say, sorry, I didn't write this in the slides. I should say I learned this completely from Berthelot's gigantic book on crystalline cohomology. In crystalline cohomology theory, they were doing this, but then doing complicated stuff uh, um, with divided powers for prime numbers and stuff like that. And if you just sort of throw out all the anything in positive characteristic from all those books on crystalline cohomology, that's what it boils down to is this construction. And so this formal groupoid represents a stack, so a family of categories over the site of scheme, like big site of affine schemes, let's say. And the stack it can be just written in simplified form as the value on y is just the value of s on y reduced. That means that if you have two different, right, if you have two different points, if you have a scheme y, let's say an affine scheme y, maybe a finite type, uh, uh, then a map from Y into the S Rham stack is a map from Y into S, but modulo the equivalence relation that two maps are the same if the pair of those maps into this formal completion of the diagonal. What does that really mean? It just means that those two maps are the same on the reduced subscheme of Y. So what you get from just looking at that is just this easy formula, which says S Rham of Y is just S of Y reduced. Then you can also do this in terms of calculation. So you can say it corresponds to a Lie algebraic structure, or sorry, that should be structure, a Lie algebraic structure or Lie-Reinhardt algebra on the tangent bundle of S. So it means you have a Lie bracket and an action of that on the functions, which is just the usual one in this case. And now we have a morphism from the scheme S itself into this stack S Rham. Right? If you have a map from Y to S, and you got a map from Y reduced to S, basically. And the fiber product with itself, that's exactly the morphism object. Okay. Now, if in the case of our morphism from X to Y, from X to S, we also have a formal groupoid in X Rham, and it has a map from X Rham to S Rham, and we can pull that back from S Rham to S. We get something which we'll call the relative Rham stack X Rham over S. That's the stack which is on over its maps to S, but over every point of S, you have the Rham stack of the fiber. Okay, so that's the family of Rham stacks of the fiber. Now, what's a bundle over the Rham stack? It's the same thing as a bundle over S together with a flat connection. Because if we go back to the picture, the infinitesimally nearby points are connected together. That tells you that if you have a bundle, you're supposed to have identifications between the fibers over infinitesimally near points, and that's exactly a flat connection. Okay. Then we can, instead of looking at just bundles over S, we could look at higher stacks over S Rham. And this stacky viewpoint gives us exactly the concept of a kind of a higher connection over higher flat connection over S, basically. Then we can take the cohomology or homotopy invariants for the relative stack over S, and these will be the usual Rham cohomology and Rham homotopy type of X over S, and these come from relative invariants of X Rham over S Rham. In other words, they descend along the map from S to S Rham, and this encapsulates really the Gauss-Manin connection on the Rham invariants of X over S. And so this gives us this just gives us like a quick way of explaining the higher homotopy coherence of the Gauss-Manin connection on rational homotopy types. And that was first investigated by Navarro-Asna, who looked at that in terms of differential graded algebras and formulas and stuff. And it's actually becomes rather complicated to transform these seemingly simple statements about stacks, to transform those into actual calculatory statements about the differential graded algebras. And so in some way the goal of this viewpoint is to avoid doing that. But you're supposed to be able to do it, but we're just like not actually doing it. Okay. Okay, so now let's go from the Rham to the Higgs picture. Higgs or Dolbeault picture. And we can sort of do we can do a deformation of to the normal cone of these formal completions of the diagonal. And we get formal groupoids, which we'll call the Dolbeault formal groupoids, which are associated to the Lie algebroids, which again have underlying bundled the tangent space of S or the tangent space of X. But in this case, the Lie algebroid structure is just completely trivial. The bracket is zero, the action on functions is zero, everything is zero. That's why in the Dolbeault cohomology, you just have the HQ of omega p, but there's no differential, there's no further differentials that are acting there. Okay, so then the formal groupoid F Dolbeault of X is just the commutative formal groupoid whose morphism object is the tangent bundle of X, viewed as lying over the zero section. So viewed as lying over the diagonal inside X cross X. So and the same for S. So basically, we've sort of tilted this formal completion of the diagonal, which is sitting inside, let's see, S cross S or X cross X. We've kind of tilted it so it becomes vertical over the diagonal. And in terms of our picture with infinitesimal loops, it means that we take each infinitesimal loop and joining two nearby points, we sort of squish together the endpoints so that it just becomes a loop based at each of those points. So the picture becomes this picture. So in this picture upstairs, these are supposed to be this. I mean, it's hard to draw the picture, but this is supposed to be a picture where the blue things upstairs are lying over the diagonal. So it's a vertical thing. It's kind of sticking out of the page, you might say. So it's the morphism object now lies over the diagonal in S cross X. There's no morphisms between nearby points. There's only endomorphisms of points. And downstairs, we can see this picture of the little infinitesimal loops having been sort of squished together. They become, instead of links, they become loops based at each point. And the loop is the thing parameterizing loops is the tangent space, because the thing parameterizing a loop from a point to a nearby point is basically the tangent space at that point. And so that infinitesimal loop is kind of being parameterized by the tangent space over S. So if you have a trivialization of the tangent bundle just in a local neighborhood, then we can write the Dolbeault formal groupoid as just S cross the Eilenberg-MacLane stack of AK hat, where AK hat is the formal completion of the affine K space at the origin. And that's a local picture, but what it means in general is that we take the tangent space, the tangent bundle of S over S, and we formally complete along the diagonal, and then take the Eilenberg-MacLane stack of that thing. So this is no longer a sheaf, this is now a stack. The Rham stack was actually a sheaf, although we maybe defined it as a stack, right? We defined it as a formal category, but it's actually just a sheaf. But now the Dolbeault thing, it really is a one stack. And now a Higgs bundle on S is the same thing as a sheaf on the Dolbeault sheaf that pulls back to a locally free sheaf on S. In other words, it's a bundle on S together with an action of the Lie algebroid, the tangent space, with the zero Lie algebroid structure. It just means that that all the different actions of the tangent vectors have to commute with each other, and that's exactly a Higgs field. And then you can again do the same thing and get a relative version. So we'll have X Dolbeault over S, and if we take the higher direct image functors of the structure sheaf on this relative Rham stack, this is exactly going to be the relative Dolbeault cohomology over S. And as we recalled before, that this can be expressed as the gradient of the Hodge filtration. So it's the direct sum of HQ omega p. That's just so this last part is just classical Hodge theory. So we're just kind of doing classical Hodge theory, but giving a stacky kind of flavor to the situation. But then what we can do is again define the relative Dolbeault homotopy type rather than Rham. For this to exist, you really want F to be relatively one connected. We'll see a little bit more precisely that in a minute. And then now whereas before we had a Gauss-Manin connection, so it meant that the Rham stack downstairs was going to act on the family of homotopy of Rham homotopy types upstairs. Now the Dolbeault stack downstairs acts on the family of Dolbeault homotopy type upstairs. Um, and in some way, that's just really, again, the graded of the Gauss-Manin connection acting on the associated graded of the Hodge filtration. Um, so we'll have infinitesimal actions of the tangent bundle, and in fact, those actually become algebraized to infinitesimal actions of the full tangent bundle, not just the formal completion at the origin. The Dolbeault stack really, the morphism object of the Dolbeault stack is really the formal completion of the tangent bundle at the origin. Whereas for Higgs bundles, we would really like to say it's actually an action of the full tangent bundle. And since it's in algebraic geometry, that works out okay. And so now this action of the action of the tangent space on the Dolbeault cohomology is just the same as what we saw at the start. It's a classical Kodaira-Spencer map on the associated graded of the Hodge filtration. However, and now we have sort of the language that's required to be able to say that we can get secondary invariants of this action in homotopy theory, and we'll call those the secondary Kodaira-Spencer classes. So now I'd like to discuss the topological setting. So in order to sort of understand what topological types of information could be contained in this type of situation, let's go back and think of just a topological setting. So suppose we just have a fibration of topological spaces, and suppose we have a subspace S prime in the base with the property that, well, for one thing, well, in fact, S prime is really going to be a torus here. But anyway, let's just suppose that the pi one of the S prime acts trivially on the homotopical invariants of the fiber, or the cohomological invariants. But now it doesn't follow that X prime over S prime is actually trivial. So the fact that if you have again, typically here S prime is going to be a torus. So if you have a family of varieties if you have a family of spaces over a torus, the fact that the monodromy is trivial along the loops in the torus does not imply that it's a trivial fibration. And so we can look at this using the Postnikov tower. You can just sort of calculate that there's going to be other invariants in the Postnikov tower. Okay, so let's just take the Postnikov tower of xk prime, and then xk plus 1 prime to xk prime is the Eilenberg-MacLane space fibration k plus 1 k plus 1, where a k plus 1 is a constant local system over the base. It's the k plus 1 homotopy group, relative homotopy group. And now we have this fibration is determined by cohomology classes. It's really going to be a cohomology class. So if you have a fibration, which is an Eilenberg-MacLane space, that's determined by a cohomology class of the base and coefficients in the island with coefficients, with a degree k plus 2, one further than the degree of that Eilenberg-MacLane space. So the structure of each level of each fibration in the Postnikov tower is given by a cohomology class of the lower element of the Postnikov tower. Now so as I said before, let's suppose the S prime is actually a torus. So its fundamental group is abelian, which is not too complicated, but on the other hand, it has an understandable but fairly large space of cohomology. This is going to help in terms of computing the secondary invariants. And because the cohomology classes governing those fibrations in the Postnikov tower, we'll be able to write those down using the Leray spectral sequence. And eventually they come down to cohomology classes on S prime, and those can be non-trivial cohomology classes on S prime, basically. And then this extends to a situation where the base is a stacky thing, such as one of our Rham or Dolbeault stacks, and the S prime, the substack, is an Eilenberg-MacLane substack for some abelian group sheaf A. Okay. And in particular, we'll be having two different cases that arise in algebraic geometry. So as we've seen above, we can take the Dolbeault stack. Then over every point, we have a gerb, which is the it's the k of the tangent space comma 1. It's the Eilenberg-MacLane stack for the tangent space at that point. So this is just as very similar to having a torus. I mean, it's the Eilenberg-MacLane space for an abelian thing. It's just not an abelian group. It's an abelian group sheaf of groups. Okay. And then a second case, which is interesting also, is that suppose that we take the Rham stack, but with logarithmic singularities along the divisor. Then you have the residue at the singular points of the divisor. We have the residues, and we can view this again as coming from an Eilenberg-MacLane stack sitting inside the. This should be S star here, I guess, sitting inside the logarithmic Rham stack. We'll be talking about that in a minute. So then this is going to give us a stacky examples of the kind of integration relationship, which is coming from variations of Hodge structure between Kodaira-Spencer Higgs fields and the transport of the connection. Okay, so let's get back to the topological picture. So suppose S, let's just replace S prime by S in our topological picture, and suppose it's a torus. Okay. Then the fundamental group Z to the K acts on the homotopy groups and the cohomology groups of the fibers. But again, as I was saying before, let's look at the Postnikov tower for this thing. This is going to have extra cohomology classes, which will have Leray components, which have the form higher cohomology classes on the base with coefficients in cohomology of the fiber. So instead of getting to a general calculation, I wanted to just discuss the case which I was able to actually calculate, which is a case where the secondary classes can be detected by cut products. So let's suppose that the fundamental group has trivial monodromy, so it's acting trivially on the cohomology. We could ask, is this fibration going to be a product or not? So if the fibration were a product, so if X was of the form XS cross S, then the Kunath formula would tell us that the cohomology of X would be the cohomology of XS tensor with the cohomology of S, and that would be compatible with cut product. So it means that if you had a class in H2 of the base of the fiber, whose cut product was 0 in H4 of the fiber, then you could lift it to a class in H2 of the total space, which would also satisfy eta cup eta equals 0. Okay. And however, in general, fibration is not necessarily going to be a product, and we'll be able to detect this by looking at the cut product. In fact, so suppose H1 equals 0 and H3 equals 0, for example. And suppose we have a base point section, then a class in H0 of the base with coefficients in H2 of the fibers lifts to a unique class in H2 of the total space, which vanishes on the base point section. And let's suppose that eta cup eta equals 0 in H0 with coefficients in H4 of the fiber. Okay. Then basically, so this is basically what's going on here is that in the Leray spectral sequence, remember that it says it converges through the cohomology, but that means there's a filtration on the cohomology, and the abutment of the spectral sequence is the associated gradient of the filtration. So the fact that we know a cut product vanishing sort of in the abutment of the Leray spectral sequence, that doesn't mean that the cut product actually vanishes in the total space. It just means that the cut product goes at least one or more steps lower in the Leray filtration. Here, the next step lower is 0 because we assumed H1 equals 0 and H3 equals 0. So it actually goes 2 steps lower. And we'll get a cut product element, which is going to be in H2 of the base with coefficients in H2 of the fiber. And so now let's apply this. Now let's go back and apply this to our case of a smooth projective morphism. So again, let's suppose that the classical Higgs field giving the action of the tangent space on the cohomology is trivial. Right, so what we want to do is we want to take this previous discussion and transpose it into the Dolbeault homotopy types, where we have a fibration over a base, and the base is the Eilenberg-MacLane stack of the tangent of the tangent space of the base. So our hypothesis that the monodromy was trivial here becomes a hypothesis that the Kodaira-Spencer Higgs field is 0. In other words, that the tangent space acts trivially on the cohomology of the fiber. But we can again look at cut products, and that comes down in this our case of eta cup eta comes down to basically looking at non-abelian cohomology with respect to with coefficients in the schematic two-sphere. The schematic two-sphere has two steps in its Bosnikov tower. It has an additive group in degree 2 and an additive group in degree 3. Okay. And the structural map for the Bosnikov tower is essentially this cut product map. It says that, yeah, right. The H4 of the Eilenberg-MacLane state space, that's the symmetric power, the second symmetric power of GA. So that's going to be O. And the structural map for the fibration of KGA3 is a map to an H, less than H4 again. Okay. We can do this in a stacky way using nonabelian cohomology. A map from the Dolbeault homotopy type S2 to the schematic two-sphere is basically a cohomology class such that eta cup eta equals 0. Then, as we discussed before, then in that case, the eta cup eta goes to a degree 2 class on the base with coefficients in H2 of the fiber. And so I actually calculated, let me do this a little quickly, calculated an explicit example of this. So suppose we can take a smooth projective surface with H20 different from 0. Then we can blow up the diagonal. So here I'll use S and Z kind of interchangeably, but Z is the fiber S and S is the base S, basically. So now what happens if we blow up the diagonal? Then we get a fibration where, right, so in other words, we get when a fibration fibered over S, where the fiber is the blow up of Z, which is S, at that point, okay? So we have a family of blow ups of the space at different points. Then we can actually choose a class, sort of chosen in the right way, such that eta cup eta equals 0. The coefficients might have to be complex numbers to solve that. Then you can show that the secondary class is a map from the wedge to exterior power of the tangent space of the base into H2 of the fiber. Let me just go back in a minute here. Remember, in the topological picture, we had a class in H2 of the base with coefficients in H2 of the fiber. In our case, the base is really the Eilenberg-MacLane stack for the tangent space. So its H2 is a wedge 2. Sorry, its H2 is its H2 is the dual of the wedge 2 of the tangent space. And then that class is exactly of this shape, basically. And the theorem is that in our example, this map is actually the Poincare dual of the evaluation map from H0 of the canonical sheaf to wedge 2 of the tangent space. And so it's non-zero. So you can get an example where the secondary Kodaira-Spencer class is non-zero. It's somewhat suggestive, although I'm not completely sure whether this actually means anything or not. But this is kind of the same example that Mumford had, where you have a variety that has kind of infinitely generated Chow group, basically, of a surface whose Chow group of 0 cycles is sort of very big. It seems like this Kodaira-Spencer class is probably related to that in some way, although I don't know exactly how. And this is kind of a small part of what we were looking at with Ludmila and Tony quite some time ago, which we called variation of non-abelian mixed Hodge structure. And our secondary Kodaira-Spencer Higgs field here is going to be the variational data. It's going to enter into that theory as part of the variational data. We can recall from that preprint that discussing the weight and purity properties was much more subtle and I think still subject of investigation, or needs to be investigated at least. Okay, so that's that part. Now I'd like to turn to the second kind of item in the list that I had before, which is the case of logarithmic connections and residues. So let's suppose we have just a disk and a coordinate, and suppose we have a vector bundle with a logarithmic connection, and suppose that the residue is nilpotent. Okay, then you can actually create a model connection on that sheaf. So just using the fiber over zero, you can actually write back down the full family, really. So namely, you can make a model logarithmic connection by taking that vector space, spreading it out over S, and defining the connection to be given by just that nilpotent endomorphism times dz over z. Then whatever our original logarithmic connection was, there's a unique isomorphism with this model connection that respects the logarithmic connections and induces the identity on the fiber over zero. We can also, well, anyway, there's another comment there. And this also works in higher dimensions. Suppose we have a k-tuple of commuting nilpotent endomorphisms, then we can again build a model vector bundle over a higher dimensional polydisk. We can assign it a logarithmic connection, and that connection, that bundle with logarithmic connection is going to be canonically isomorphic to the original vector bundle with logarithmic connection. And this is actually this construction is you might say basically in my view at least the first step in the classical nilpotent orbit theorem for variations of Hodge structure. We're sort of unwinding the nilpotent monodromy essentially, and it's basic to Deline's lecture notes in math on regular singularities. So this implies that the category of logarithmic connections with nilpotent residues satisfies strictness, so it forms an abelian category, and in fact, it's also has tensor product, so it's actually a Tanakian category. And in some way, the observation, which is kind of inspiring what we're discussing here, is that you get a fiber functor by taking the fiber over the origin of a logarithmic connection. That's a fiber functor, which of course is isomorphic to the fiber functor of fiber over some other point. But it's not completely clear how that actually works. I mean, it's kind of a somewhat subtle, new, different fiber functor on the category of vector bundles with nilpotent endomorphisms. Then we can make another observation, which which we showed with Jaya Ear in the preprint version, the archive preprint version of one of our articles from 2006. Which is that suppose it's somewhat related. So suppose we have a perfect complex on S with logarithmic connection. So what that really means is a perfect complex on this, what we'll see in a minute, the logarithmic de Rham stack. And suppose that the residues act nilpotently on all the fibers of this perfect complex. Then you can show that the perfect complex splits as a direct sum of locally free sheaves. The basic reason for that is that if you want to, you can have perfect complexes that definitely don't split as direct sums of vector bundles. Of course, the complexes, but I mean as a perfect complex. But in that case, then you have a differential, and it turns out that if you had a kind of a differential that was going to zero at the origin, then that would have to induce a pair of eigenvalues of the residues, which would differ by an integer. So if all the eigenvalues are zero, then you can't have pairs that differ by integers, and that's the basic reason why in that case the perfect complex has to split as a direct sum of vector bundles. Okay, so using those observations, we can then kind of extend our theory to the case of logarithmic de Rham stacks. So let's suppose we have a smooth complex variety and a divisor with normal crossings. Then we can define a formal groupoid, a logarithmic de Rham formal groupoid. So in terms of Lie algebroids, we can say this is associated to the Lie algebroid that's given by tangent vector fields that are tangent to the divisor D. We get a stack that could be called the logarithmic de Rham stack, and this showed up in recent preprint by Michael Bars in December. We can draw the picture in one dimensions again, somewhat similar. It's sort of in some way a deformation from the Rham stack to some Dolbeault type of stack at the origin. Although it should be noted that the fiber at the origin, it's not the tangent space, it's actually the logarithmic tangent space, which has the canonical basis vector. So that's not exactly the Dolbeault space. But anyway, the picture is this. So these points which are different from the origin get linked to infinitesimally close by points. But at the origin, the point just becomes linked to itself, basically. And in terms of the formal category, the formal completion of the diagonal gets sort of twisted over the origin to become vertical, basically. So, I mean, algebraically speaking, maybe it's easiest to work with the Lie algebroid in this case. And again, we have a morphism from S to the logarithmic Rham stack. The fiber product is the morphism object, which we just saw. If you have a so the divisor is going to have a stratification by multiple intersections. And the Lie algebroid over one of the strata, it's an extension of the Rham stack of the strata by what you might call a residue vector bundle. The residue vector bundle is the space of tangent vector fields that actually vanish along the stratum. And this R thing that represents the residues in the transverse direction to the stratum, basically. Then if we have a morphism, we also get a relative version of the Rham stack of X mapping to S. And so now let me just do a little kind of a little side discussion about complex schematic homotopy types. So in order to deal with these stacks, and this was kind of already present in the previous discussion. So what we'd like to work with here is schematic homotopy types. These are n stacks. Let's say if we're talking about n truncated schematic homotopy types, there are going to be n stacks with some restrictions on the homotopy group sheaves. If we're talking about relatively simply connected things, then all the local choices of base points will be the equivalent, and we can talk about the homotopy group sheaves without talking about the base point. And so what do we make as a condition? So in our case, it suffices to make the condition that the homotopy group sheaves should be represented by finite dimensional affine spaces, vector spaces, in other words. Or another way of writing this is you take the structure sheaf over the big site and take powers of the structure sheaf locally. There's a terminology of connected very presentable geometric n stacks, which is a little bit more general. But in our case, actually, it turns out that we don't need to use that greater generality, because we can just restrict to the case that the homotopy group sheaves be locally free O modules, even in a relative situation. So even relatively speaking, we're talking about things which are relatively one-connected, but then over the base, there's going to be a sheaf kind of operation. But which in principle, the dimensions of these things could actually jump, and that's this very presentable thing. But in our case, it turns out, for the reasons about the nilpotent logarithmic connections that we saw before, it turns out that you don't actually have this jumping situation. This was studied by Lumil, Tony, and Bertrand Toine, the schematization of the homotopy type, and they put a Hodge structure on it. In the simply connected case, we can think of the schematization as just taking the rational homotopy type and tensoring with C, basically, in kind of a pretty basic way. In other words, the homotopy groups are just tensored with C. And that can be viewed as the universal schematic homotopy type with a map from X to that thing. Okay, the universal property defines a representing object for other stacks also. such as the things we've been looking at, the Rham, Dolbeault, or logarithmic Rham stacks. And the basic requirement to get representability is that the first cohomology of F of our stack with coefficients in O should be 0, which is, I mean, basically simply connected, but you just really need to be simply connected for maps to additive group schemes. Okay. Then you could do calculations, although, as I said before, we're trying to avoid doing any calculations here. But if you needed to do calculations, then you would have models for these things, which would be either DGLAs or CDGAs, which would be, but defined over the complex numbers rather than over the rationals. So suppose we have an n stack over the logarithmic Rham stack with the property that when we pull back to S, we have a relatively one-connected n stack whose homotopy group sheaves are locally free. Okay. Then the fact that it came from a stack over the logarithmic Rham stack, it means that we have an action of the Lie algebroid, basically. The restriction to one of the strata comes with an action in particular of the Ri, this residue thing. And now this is a situation which was very similar to the higher Kodaira-Spencer classes, because the residual directions, that's a commutative unipotent group scheme that, you know, it's inside the Lie algebroid, it has zero coefficients of the Lie algebroid structure. So that's very similar to just having a Higgs field, basically. And so this is going to act, but in the sense of a higher action on the homotopy type over the base, over that point. So now a typical situation in which this is going to happen is when we have a semi-stable family. The family is semi-stable if the map is expressed by monomials where each coordinate upstairs appears at most once in a coordinate downstairs. That's a little bit stronger than saying that the divisor downstairs pulls back to a reduced divisor upstairs. So I mean, you're sort of throwing out the possibility of blowing up stuff. The last thing I just said would also hold for blowing up a point, for example, but that's not allowed as a semi-stable map. Okay, so there's kind of a major development in algebraic geometry, which has happened fairly recently, has been the proof of the semi-stable reduction theorem for higher dimensional base and higher dimensional fibers, right? So that was known for one-dimensional base and higher dimensional fibers, and was known for higher dimensional base and one-dimensional fibers for quite some time, but only fairly recently do we have a full semi-stable reduction theorem in general. So this was proven and finally proven by Adipasito, Liu, and Temkin, and it came from ideas of Abramovich, Caro, and Abramovich, Temkin, Lodarchik. The theorem says that a general morphism has a semi-stable model after what you call alterations, which is to say ramified and then birational modifications of the base and birational modifications of the total space. So because of that theorem, we can now suppose that we have a semi-stable fibration, of course, up to those modifications, obviously. Now let's take the singular divisor. So now let's look at the normal crossings divisor here, divisors, and then we have the relative formal groupoid that comes with a descent to the logarithmic Rham stack. And we can look at the relative schematic homotopy type of this fibration. Okay. So if we assume that the smooth fiber is one connected, then I should say assume here, but actually it's actually a consequence, I should say, that over the singular fibers, we also have the vanishing of the H1 because of that property of nilpotent logarithmic connections. Then we have a homotopy type of the relative logarithmic Rham stack, which is going to be a universal object fitting into a diagram like that. Okay, and so each fiber of this T over S is going to be the Rham homotopy type, the logarithmic Rham homotopy type of the fiber. Okay, if we have a point in one of the strata, then the residue acts on that homotopy type. The residual space is a k-dimensional complex vector space, and it means we have an action. So having an action really means having a fibration sequence with some total space mapping to the k pi 1 space of the of that group, and then the fiber is TS. Okay. So let's by taking transverse slices, we can always kind of assume that we have that we're looking at a zero-dimensional stratum of S of the divisor. So let's just suppose that S is a zero-dimensional stratum. Then the fiber over S is a union of strata that we'll denote by xj. And these strata have their own Lie algebroids. And we can just kind of glue together the Rham stack by gluing together these Lie algebroids over the pieces of the fiber. I mean, yeah, as a first approximation, although that's not really what we're talking about here, but first approximation, think of a family of semi-stable family of curves. The logarithmic Rham stack of the central fiber is going to be obtained by gluing together logarithmic Rham stacks of the pieces, and identifying the residual spaces at the group together at the nodal points. So the point here is, in the case of a semi-stable family in higher dimensions, that gluing process also fits together, gives you a way of fitting together a logarithmic Rham stack. And so then we can get a representing schematic homotopy type of the resulting glued stack. Now, on the other hand, we can also look at the link around that point, which is a small torus. It can be described. Sorry, that shouldn't be boundary. It's like the multi-boundary of the k-dimensional polydisk. It's not the boundary; it's the multi-boundary. Take a nearby point, and so we're going to get a fibration of just a k-dimensional real torus. We're going to get a fibration over a k-dimensional real torus, and the fiber is the general fiber, right? So that's the homotopical situation we were considering at the beginning. So you might say what we're doing in this talk here is we're saying, okay, suppose we have a semi-stable family, then you can look at a nearby point to a point like, so let's say, a zero-dimensional stratum of the base. On that nearby point, you'll have a little nearby torus. Then you'll have the fiber over that nearby point. It will sort of have a monodromy action of the torus in some way, but it's a homotopical monodromy action of the torus. Then on the other hand, you'll have the residue thing, which is the central fiber. And that's going to have sort of a stacky monodromy action of the residual space at the origin. And we'd like to compare these two. So we have the schematic homotopy type of the nearby fiber, and we also have the schematic homotopy type of the representing homotopy type of the logarithmic Rham stack of the central fiber. We have, I shouldn't say the same homotopy type. I mean, we have two different homotopy types with different actions of the abelian group. We claim that those are equivalent. So that's done. Then, if we wanted to look at a general stacky situation over the base, we would make the hypothesis that the actions of the residues are nilpotent, and that's going to hold in the case where we have the representing homotopy type for a semi-stable family. Oh, basically by Alan Landman's thesis. Phil Griffiths will remember that was my undergraduate project to read that. And there's a spectral sequence argument there, which basically shows the nilpotency of the monodromy action. Okay, so then under this hypothesis, because of the properties that we said previously about logarithmic connections, the cohomology group sheaves and the homotopy group sheaves of our schematic homotopy type family are locally free. So suppose we have a polydisk, then just as for the case of logarithmic connections, we can actually just make a model using we have the central fiber T0 has an action of the vector space R0, and we can just make a model for that action on the homotopy group, on the homotopy type. Creating that model is actually relatively easy in this case. You can just look at a canonical map to the R01 space and just pull back the TR. That gives you a model. There's a step to go from the R0 hat to the R0, especially if you want that model to also work for the Betty homotopy type of the base. Anyway. Then the theorem is that the restriction to the stacking point at the origin is actually an equivalence of categories between one connected schematic homotopy types over the logarithmic disk and things over just the stacking point at the origin. In particular, given our model, there's a unique isomorphism between our model and our original family of homotopy types. And so what's the corollary? The corollary is that suppose we have the homotopy type of the fiber, then it's going to be isomorphic with its monodromy action of the nearby fiber with its monodromy action is going to be isomorphic to the homotopy type of T0 with the action of R0. And then let's see, I guess I didn't say this, but if we just go back to in particular, that applies to this case of semistable fibrations. That's what I'd like to say here. So this corollary applies to the case of semistable fibrations. So this tells us that the nearby fiber with its mapping to a little small nearby torus, that the secondary invariants of that thing can be calculated as sort of algebraic geometry secondary invariants of the action of R0 on the homotopy type of the fiber. Let's see, so that's what I wanted to say, and I just want to do a last slide here with further directions. So here we haven't discussed anything about the Hodge filtration in this discussion. As I said before, the case for just Sheaves local systems was the starting point for the nilpotent orbit theorem. So it should be possible to compare the Hodge filtration that you get in the algebraic geometry case with this limiting secondary Kodaira-Spencer class. There should be kind of a version of the Clement-Schmidt exact sequence for homotopy theory, basically, somewhere. There should be mixed Hodge structures here and everything. We would like to do this. We would like to remove this relatively simply connected hypothesis, but that's going to be what the situation that's going to be happening there is a lot less clear, and that was the subject of many discussions with Ludmil and Tony about what we were calling the non-abelian. We didn't really have a definition, but that we're looking for the non-abelian Clement-Schmidt exact sequence. Somehow they're in the case where it's not simply connected, relatively simply connected, then the family of character varieties, moduli spaces of G local systems, has a very complicated degeneration structure, and it's not very clear cut at all. I don't think how to do this. The thing what you did here at the end of the argument, where we said we have a local model just by sort of pulling back, you can't do that for character varieties. And it's pretty unclear even what exactly is the space that we would like to really put in the middle of this fibration, basically. And then a different direction is also, I'm sorry, but I don't actually have any examples of cases where we have the secondary residue, so I think it would be good to have examples, and I apologize for not having any examples so far. Anyway, okay, so I'll stop here.